Hello. Hi. If you're there, make sure that you say hi in the chat. Please introduce yourself. Oh, hi, Ishak. Hi, Holika. And hi, Lily. Hi, Grace. Yay. Okay, lovely. Make sure that you're saying hi. Me too. Hi, away. Okay, we'll start when it gets to 11. But for now, again, make sure you're introducing yourself. If I've ever taught you in real life, make sure that you say hi as well. I miss you already. Hello, hello. Hi, yay. Okay, great. So many of you. And we're starting with everyone's favorite topic, which is moles. I can hear you all celebrating from home. Yay, moles. Oh my God, my favorite. Oh no, I love moles too. Moles are my favorite. I need to bring in, I have a hat that says, when in doubt, moles. So I agree. Great. And if you don't like moles, hopefully by the end of this lesson, you will love them because it's so, so key to pretty much the whole of A level chemistry. They put them in everywhere. So the more comfortable you feel with them, the better. Okay. So now that it's 11 morning, hello. So now that it's 11, we're going to get started. Again, make sure that you say hi as you're coming in. Um, and make sure that you type in the chat, ask any questions. We might get through the content before the time is up. So if you have any questions on the topic, any types of calculations that you've seen on your travels that you've struggled with, make sure you let me know. I've got a few blank slides at the end that are there specifically for your questions. Okay. Make sure you've also got the workbooks. Hello, hi. So that you can follow along and do the calculations as we're going. And again, questions as you're going as well. So let me briefly introduce myself. Hi, I am LaJoy Tucker. Hi, I am a fully qualified chemistry teacher. I've been teaching for 10 years now. I know I don't look it. I don't look a day over. I'll let you fill in the gaps. Okay, I studied chemistry at Oxford University and I got a first class undergraduate master's degree, which is called an MChem when you study it there. And at A level, so my three A levels were biology, chemistry, and maths, and I got three A stars. And I also did two AS levels in English literature and French and got A's in those. Okay, but chemistry obviously is my favorite. I love it. Hopefully, you will all love it too if you don't already. So as I mentioned before, our first lesson is on stoichiometric relationships, which essentially means moles, okay, how we relate moles of one species to another. And so we'll go through some of the core calculation types. Um, Again, if you find it really, really simple, great. If you are struggling through it, again, great, because hopefully by the end of it, you'll feel a lot more confident. So Are you ready? Do you have, actually, first of all, you're going to need calculators. I might be asking you as well for some of your numbers, so make sure that you have a calculator to hand. Make sure you've got your work pack so that you can work through the questions as we're going. Okay, everyone ready? I want yays and thumbs ups and smiling faces in the chat, please, and thank you. I'm not starting until yay. Okay, lovely. Oh, amazing. Okay, great, great, great. Wonderful. Fantastic. Let's go. Okay. So, as I mentioned before, when we're talking about stoichiometric relationships, we're essentially talking about the ratios between the reactants and the products. And the coefficients, of course, so those numbers, those letters rather, that I've got in red, those tell us the ratios. So, the stoichiometric relationships. When you see the word stoichiometry, it basically just means ratios. Okay. So, when in doubt, and I'm going to be saying this a lot, and I hope that you will start to say it with me. When in doubt, moles. Okay, I know it doesn't rhyme, but that's my favorite saying, and I'm going to say it over and over again. Whenever you're in doubt about a calculation, go to moles, and you'll get at least something out of it, even if you get stuck before the end. And there are, of course, multiple ways that we can calculate moles. The most straightforward one, the one that we see the earliest, so just from GCSE, is using mass. So, oh, come back. There we go. So where moles are equal to mass divided by the MR. Then solutions, that's what we typically see next, where moles equals concentration times volume. And then gases, that's what we are introduced to really at A level using the ideal gas equation. So once you found the moles of one thing, whatever in the question you have enough information to find the moles for, you then look at the ratio, so the stoichiometric relationship. Oh, to tell us the moles of the second thing that we care about. And then we use whichever expression we need to find whatever it is we're trying to find out, if that makes sense. Okay, so we'll go through a few examples now. Again, the first few I would say follow along with me, and then we'll do a few more that you can just kind of have a go at, and I will try and stay silent while you actually have a go at them yourselves. Okay, again, any questions in the chat at any time, please put them in there. So let's start with a nice and straightforward one. If we start with a mass and we're trying to find a mass, so we've got 47.6 grams of ammonia reacting with excess HCl, calculate the mass of the ammonium chloride produced. So when in doubt, find the moles, and we'll find the moles of what we have enough information to find the moles for, which in this case is the NH3. So the moles of NH3. And I always lay out my calculations in the same way. So when you're doing calculations, don't leave any number unlabeled. Even if they're really straightforward calculations like this one is, it's important to get in the habit of labeling every single number because number one, it helps you check your work because even I make mistakes after all of these years of doing chemistry. So it allows you to go back and check that you've done it correctly. And also whoever's marking your work, because, we are trying to get ready for some exams as well, they can really clearly follow your calculations. And if you do make a mistake, they can give you some error carried forward if there are any issues. Okay, so let's get back into it. So moles of the ammonia, mass over MR. So your mass, that is 47.6. And then your MR from the periodic table, which I'm hoping you all have just like in front of you as a whole wall of your bedroom or oh, I'll answer that in a second. The whole wall of your bedroom should be the periodic table at this point, but there is definitely error carried forward in A level. So when you're doing calculations, there will be error carried forward for each. Well, not necessarily for every step, but there definitely is some. So you don't have to worry about that. Okay, thank you very much, Orla. The MR is indeed 17. Specifically, I'm going to say 17.0 because at A level, all of our relative atomic masses, we get to one decimal place. So again, feel free to put answers in the chat if you are beating me to it, but we should end up with 2.8 moles. I hope that you agree. Wonderful. Then that's the moles of the NH3. Oh, Zakir, again, I'm going to come back to that question in just a moment or back to that point. So to find out the moles of the ammonium chloride, we want to look at the ratio. Here it's a 1-to-1 ratio, which means that the moles of the ammonium chloride are going to be the same as the moles of the NH3. So also 2.8. And so now to find the mass is equal to moles times MR. So your moles, 2.8, multiplied by the MR. I like to do a bit of a side quest sometimes just to show the working, rather than, again, trying to plug all the numbers in at the same time, because I tend to make mistakes that way personally. So that's 14 for the nitrogen, plus 4 from the hydrogen, plus 35.5 from the chlorine, which gives us 53.5. Um, and then multiply those together, again, showing every step of the working, and we should get 149.8 grams. Okay, now in this question, wonderful, in this question, it hasn't specified how many significant figures to give your answer to, but often they do say give your answer to an appropriate number of significant figures. And the appropriate number of significant figures is whatever the least number of significant figures are that you have in the question. So here, the mass that we've got for the ammonia, 47.6, that's to 3 significant figures, which means that ideally our answer should also be to 3 significant figures, which rounds to 150 grams. Okay, are we happy with that? Coming back to your point, Zakir, about ECF, so error carried forward, it depends on where the errors are, okay, because errors carried forward will depend on what you did previously. So there is a way that you might not get error carried forward in a particular question, but if in doubt, moles, but I would recommend maybe going and just double checking with your teacher or double checking with the mark scheme if you know what paper that question was from, to see if there is actually error carried forward that can be or should have been assigned to that question. Anaf, you wouldn't lose marks if you didn't do it to 3 significant figures in this question, only because the question doesn't specify give your answer to an appropriate number of significant figures. But if it did say that, then you wouldn't get the final mark if you gave it to the wrong number of significant figures. Okay, so they'll say if they really want you to, but it's good practice just to do it anyway because that's the correct thing. Okay, let's go to the next worked example. So here we've got mass to solution. Again, when in doubt, find the moles. So what volume of 0.150 moles per dm cubed HCl is needed to completely react with 34.7 grams of calcium carbonate? So the first thing that we want to do is figure out which of these two we can find the moles for. Of course, we're trying to find out about the HCl, so we're going to start by finding the moles of the calcium carbonate. So the moles, again, labeling every single stage. Moles of calcium carbonate, that's again your mass over MR. So mass 34.7. MR, I chose calcium carbonate because I know this MR off by heart is 100.1. Okay, but if you don't believe me, feel free to double check with your periodic tables. And we end up with, again, if any of you are faster with your calculators than me, please let me know. Oh, well, that's easy. 0.347, essentially. Then we look at our ratios to figure out how many moles of HCl we should have. Here we have a 1-to-2 ratio, which means that your moles of HCl, I'm just going to put 1-to-2. So your moles of HCl are going to be 0.347 times 2, which is 0.693. Okay, again, let me know if I make a mistake. It happens. I am just a human being. Okay, that's your moles of HCl. So now we want the volume of the HCl. I've given you a hint. Well, it's a massive hint with this formula triangle up in the corner where moles are equal to concentration times volume, which means that volume is equal to moles divided by concentration. So our moles, 0.693, divided by our concentration, which was 0.150. I times by 2 because of the ratio. So the calcium carbonate to HCl is a 1 to 2 ratio. So one mole of calcium carbonate reacts with 2 moles of HCl. So we have to make that change. 0.694, again, it depends on how you rounded in your calculator. I kept the whole number that I got from here and multiplied that by 2. So using answer, and I ended up with 0.693 because of how this rounded. But if you got 0.694, that is absolutely fine because you've used this number. That's fine. Okay. So now we can put that number again, whether you got 0.693 or 0.694, divide that by 0.150, and you should end up with 4.62. Perfect. Okay, now the units. Can anyone tell me what are the units, please, for this volume? Anybody? Perfect. The units are in decimeters cubed. Okay, again, in this question, it hasn't specified whether they wanted the volume in centimeters cubed or decimeters cubed. Amazing. Oh, you guys, you're so good. It hasn't specified whether they wanted it in decimeters cubed or centimeters cubed. So you can give it in either as long as you put the units there. So if you just wrote 4.62 and didn't put any units, you probably wouldn't get that last mark. Okay, because you haven't specified which units you've got. Okay, so 4.62 decimeters cubed, or if we wanted to turn that into centimeters cubed, what's our conversion? Decimeters cubed, centimeters cubed. Conversion, lovely. Multiplied by 1,000, great. So we should end up with 4,620. That's a massive volume. Wow, almost 5 liters of HCl to react with that calcium carbonate. Okay, great. Again, we haven't specified in the question whether we want that volume. Sorry, let me learn how to speak. It hasn't specified in the question that they want it to a particular number of significant figures, but it's always good practice to give it to the appropriate number of significant figures anyway. The volume is given to 3 significant figures, and the mass is also given to 3 significant figures. So our answer also 3 significant figures. Okay, this would probably be 2 to 3 marks. Okay, because it is relatively straightforward. We're going to get to some of the trickier ones shortly when we start to talk about limiting reagents, which so many people hate, and I understand why. Okay, but we're going to work strategically through it. Okay, ready for the next one? Last worked example before you do a bunch yourself. Okay, solutions to gas. So we have what volume of hydrogen gas is produced when 30 centimeters cubed of 0.2 mole per dm cubed HNO3 reacts with excess magnesium at 300 Kelvin and 101 kilopascals. So here we're using two expressions to link to moles. We're using moles equals concentration times volume to deal with our solution. And then, oh, I'm hiding it. There we go. And then we're using the ideal gas equation, PV equals nRT, to link it to the volume of gas that we need. So we've got enough information to find the moles of the HNO3. So that's where we're starting. Again, labeling everything. Moles HNO3, that's concentration times volume. Concentration 0.20. Volume needs to be in decimeters cubed, so that's 30 over 1,000. And that gives us 6 times 10 to the minus 3. Okay. Now we're using our ratio to find out how many moles of hydrogen that would produce. So here we're looking at the HNO3. We're not looking at the magnesium because that was in excess. So that's not going to determine how much hydrogen we can make. So it's a 2-to-1 ratio, which means that we're going to, so 2-to-1. So we're going to divide the moles by 2 to get the moles of H2. Okay, so we end up with 3 times 10 to the minus 3. Okay, now from this question, we want to calculate the volume of hydrogen gas. And so when we're dealing with a gas, we're going to use the ideal gas equation. So volume, PV equals nRT. So we'll rearrange that. V equals nRT over P. Now, before plugging any numbers in, because the ideal gas equation and where most students make mistakes is with the units, I'm going to go over to the side and make sure that all of the units are what I want them to be before plugging them in. So moles, we've already got 3 times 10 to the minus 3. R would be given to you in the question, which is 8.31. T should be in Kelvin, which they've already given it to you, 300. And pressure should be in pascals. So that's going to be 101,000 pascals. And now we can plug those into our expression. Absolutely, meters cubed for volume. Okay, plug those all into our calculator. Oh my gosh, why is my pen doing that? That's okay. Okay, put those all into our calculator. We get a number, okay? At the moment, doesn't necessarily matter what that number is. Fine. So our answer, as you've correctly said in the chat, is going to be meters cubed. In this question, they haven't specified what units they want the volume in. So leaving it in meters cubed is fine. But if they did want it in centimeters cubed, please let me know in the chat what the conversion is. Okay. We are, yes, the ratio between the HNO3 and the H2 is correct, 2-to-1, because the magnesium is excess. And so the HNO3 is limiting and is going to determine what volume we get or what moles we get. R is the gas constant, 8.31 joules per Kelvin per mole. And they'll give that to you in any question. Okay. Absolutely, for your conversions, well done. Times 10 to the power of 6. 8.31 or 8.314, either are absolutely fine, depends what they give you in the question. If they give you 8.31, use that. If they give you 8.314, use that. Lily, for this question, we know that the HNO3 is limiting because they've explicitly said that we're reacting with excess magnesium. So the HNO3 is what's going to determine the moles. The only time that we need to actually figure out which one is limiting, and we're going to get onto that in a bit, is if they give us information for both reactants, and then we need to find out which one is limiting. But if they only give us information for one reactant, we can assume that the other one is in excess. Okay. Okay, great. Let's go to, well, it's your turn now. Okay, so is it 74 centimeters cubed? It might be. That's a good question. When using the equation, the answer, yes. So the volume, when we're using the ideal gas equation, if we use all of these units as they should be, so pressure in pascals, temperature in Kelvin, 8.31, then the volume always comes out in meters cubed. Okay, let me double check what the answer should actually be. I definitely, let's see, here's one I prepared earlier. Oh, yes, 7.4 times 10 to the minus 5 meters cubed, and then 74 centimeters cubed to 74.0 to three significant figures. Again, looking at this question though, what would be the most appropriate number of significant figures to give your answer to? Absolutely. Yeah. Two significant figures because our volume is to two significant figures and our concentration is also to two significant figures. So even though our pressure is to 3, we always use the least number of significant figures. Okay. Again, in this question, it didn't ask for it specifically, so you wouldn't lose any marks for giving it to three significant figures. So not unless they say. So if they say, give your answer to an appropriate number of significant figures, then you would lose that final mark. But if they don't say that, then you're fine. Okay. But again, it's good practice anyway, just to stick with, oh, sorry. The answer was 7.4 times 10 to the minus 5 meters cubed, or 74 centimeters cubed. Okay. Are you ready for me to be quiet and for you to have a go at a couple yourself? Yes, no, maybe so. Wonderful. Yes, yes, yes. Great. Okay. So I'm gonna ask you two. Wonderful. Okay, you all sound really confident. Um, have a go at one of these or all of these. They get progressively more challenging. So the first one is like the most straightforward, just your mass to mass. And then the last one, when we're going to use the ideal gas equation, is the trickiest. So don't feel like you have to work your way through ones that you feel confident with already. You can just pick the hardest one that you want to practice. Okay, I'm going to give you, how long do you reckon? Is 4 minutes too mean? Let's come back. 5 minutes. That's okay. That gives us a nice rounded. So at 11:30, perfect. 11:30, we'll check through the answers. So again, that gives you time to do one of these questions. So pick the one that is going to challenge you. Don't pick one that you feel like you can already do with your eyes closed. Okay. And if you have any questions while you're working, then please put them in the chat. Yes, butene is C4H8. And we can assume in the first question that it's in excess oxygen. I will not be revealing any answers just yet, just to make sure that everyone has a chance to have a go. But I will let you know very soon. Okay. But if you are finished with one, and you did that really speedily, so really well done, Ola. Not that I'm confirming or denying that that was correct. Have a go at the next one. Yeah, have a go at question three, the third one, seeing as you've got some more time. Um, do you mean, Lily, when calculating the MR for the carbon dioxide? So we only use those the coefficients for the ratio, and then you can ignore it. So just treat it as CO2. So just one carbon, two oxygens, because the scaling you would have done already by using the ratios. Okay, no problem. Okay, we'll go for about 30 more seconds. So hopefully that gives you time to finish off one question. If you need more time, let me know. Okay, let's come back together. What I'm going to do, I'm just going to write the answers in the boxes. And if there are any of these that you want me to go through, then let me know. Okay. So for the first one, and if you disagree with me, also please do let me know. Charlie, I will get to your question in just a moment. Okay. So for the first one, 14.5 grams. Um, Charlie, when working out the moles of lead nitrate, would you times by two? Okay. So for the third one, because we're trying to find out the moles of oxygen from the lead nitrate and it's 2 to 1, we need to divide by two to get the moles of the oxygen. So however many moles of lead nitrate you start with, you're going to produce half as many moles of oxygen. Okay. Absolutely. I'm going to show you the answers for the next two, and then we'll go through whichever ones you want me to go through. Okay. So for the second one, Um, well, this is my answer again. If you disagree, let me know. I got 60.0 decimeters cubed. And then for the last one, 1.5 times 10 to the minus 4 meters cubed, or you can multiply that by 10 to the 6. Okay, so already we're definitely going to go through the first one. We're going to go through the second one. Do you want me to go to through the third one as well? We can go through all three. Okay, perfect. Let's go through all three. So for the first one, we're going from mass to mass. We're starting with 4.60 grams of butene. We're trying to find out what mass of carbon dioxide. So our first step, we've got enough information for the butene. So that's what we're going to find the moles for. So the moles of your C4H8, that's your mass over MR. Mass is 4.60. The MR, we can just do that over to the side to make sure we don't make any mistakes. That's going to be 4 times your 12 for the carbon, well, 12.0, plus 8 times 1. What's that? I should be able to do that in my head. 56. Okay. And that should give us 0.082. Okay, with me so far? Now we want to find the moles of carbon dioxide because that's what we're ultimately trying to find out the mass for. So between the butene and the carbon dioxide, it's a 1 to 4 ratio, which means that for every 1 mole of butene, we're going to produce 4 moles of carbon dioxide. So to get the moles of carbon dioxide, we need to take the moles of butene and multiply that by 4 because of that 1 to 4 ratio. Okay, and when we do that, plug that into our calculator, we get 0.33 moles. Okay, absolutely, 0.328 or 0.33. Again, you can write down as many of the numbers from your calculator as you want to, as long as you keep the whole number in your calculator. Now we've got the moles of carbon dioxide. To find the mass of carbon dioxide, that's moles times MR. So 0.33 or 0.328, keeping that whole number in your calculator, multiplied by the MR of carbon dioxide is 44. So 12 from the carbon plus 2 times the 16 from the oxygen. And then that should come out to 14.5. Okay, are we happy with this one now? Or any further questions before we go to question 2? Great. Lovely. Okay, moving on in 3, 2, 1. Next question. Okay, so question 2, what volume of HCl, so that's what we're trying to find out, is required to neutralize 15 kilograms of calcium carbonate? So we've got enough information to start with the moles of calcium carbonate because we've got the mass, so we can use mass over MR to find the moles. Okay, so moles of calcium carbonate, that's mass over MR. So 15, I'm going to turn this into grams, 15,000 grams. Okay, whenever you've got a mass that isn't given to you in grams, turn it into grams first. Okay, they love to chuck in a kilogram. They love it even more to put in a milligram. Okay, so keep your eyes peeled for those. Okay, so 15,000 divided by the MR of calcium carbonate, which we identified before was 100.1. And that gives us roughly 150 moles, right? Now, using our I can't speak, stoichiometric relationship, so our ratio to find out how many moles of HCl. So we can see here the calcium carbonate to the HCl is a 1 to 2 ratio. So for every 1 mole of calcium carbonate, we need 2 moles of HCl, which means that your moles of HCl are going to be two times the moles of your calcium carbonate, so 300 moles. Okay, and then finally, because we want the volume, volume is equal to moles over concentration. So again, using our formula triangle, moles equals concentration times volume. So volume equals moles over concentration. So moles 300, volume, oh, hang on, sorry, concentration 5.00. And then that gives us 60.0 decimeters cubed. Okay, 3 significant figures. If we wanted this in centimeters cubed instead, we could multiply that by 1,000. Okay, are we happy with question 2? Lovely. Great. Wonderful. Okay, and now question number 3. What volume, 59.9, would it be accepted? Again, if you kept all the numbers in your calculator. Oh, and what was the, Charlie, what was the next number after 9 in your calculator? Then 59.9 is absolutely fine. Yes. Um, Enough, you don't have to convert to centimeters cubed because in this question it hasn't specified. But if they did ask you for centimeters cubed, then you would have to. Okay. The brackets, Harlem, which brackets are you referring to? Oh, do you mean in the formula? So these brackets. Okay. Yes, so the brackets tell you that there are 2 lots of nitrate ions. So the NO3 sticks together, and so the lead was 2 plus, the nitrate is 1 minus, so you need 2 nitrates for every 1 lead ion. And then the 2 outside tells you it refers to everything inside the brackets. So 2 nitrogens in total and 6 oxygens. Okay. So for this one, we're trying to get to a volume of O2 and we're given the mass of lead 2 nitrate. So the most sensible place to start is to find the moles of the lead nitrate using mass over mR. You're welcome. So mass 4.00 grams. MR, I'm definitely going to do a side quest to find the MR. So we've got 1 lead, 207.2. We've got 2 nitrogens, and we've got 6 oxygens. Lovely. Thank you, Henry. 331.2. Do I agree? I agree. Great. Thank you. Okay, Ryan, double check your calculator. Oh, perfect. Okay, typo. Never mind. Well done. Okay, so 4 divided by 331.2, and we get 0.0111. Okay, again, if you disagree, please shout at me by typing in capitals. Okay, so now, yes, when calculating the MR, you ignore the big numbers. The big numbers are just for our ratio, so we can then look at the relationship and find out how many moles of the other thing we need. Okay, so here, let's pretend that this arrow was in a regular place. We have got the moles of the lead nitrate. We're trying to find the moles of the oxygen. So we can see it's for every 2 moles of lead nitrate, we get 1 mole of oxygen. It's a 2-to-1 ratio. So to find the moles of O2, we're going to divide. Ah, hang on. That might be my calculator error. Thank you. 4 divided by 331.2. Yeah, you're absolutely right. 0.0121. Thank you very much. Excellent. Okay. So to get the moles of oxygen, that's going to be half as many moles of the lead nitrate. So 0.0. Oh, in that case, that might be why. Oh, so maybe I made a mistake. Oh my goodness. I mean, I definitely made a mistake. Let's see. 0.0121. So some of your answers, your final answers might be correct, but you thought they were incorrect because I was incorrect. Let's see. Divided by 2. Point, yeah, absolutely. 6.04 times 10 to the minus 3 moles of oxygen. Then to find the volume, we know that we're going to use the ideal gas equation. And it's always worth writing out the ideal gas equation because they don't give it to you in the question. It's worth a mark just for writing it. Okay. And then rearrange. V equals nRT over P. Before putting any numbers in, we're going to, of course, make sure that all of our values are in the correct units. So moles are already fine. 6.04 times 10 to the minus 3. R would be given to us in the question. Sorry, I didn't give it to you before. 8.31, but we know that anyway. T should be in Kelvin. So 35 plus 273. 308. And pressure in pascals. So multiply kilopascals by 1,000 and then put those numbers in. Okay, with those values, did anyone put those values in the first time? And if you did, what was your answer? It should be close to the one that I put. Oh, so the same as my answer. So it didn't change it too much. So 1.5 times 10 to the minus 4. And don't forget units, meters cubed. Absolutely great. And if we were asked to give it in centimeters cubed, then multiply by 10 to the 6. Again, this question hasn't specified that, so it's absolutely fine to leave it as it is, as long as you put the units there to show what you're doing. Yes, if whatever they give you on the data sheet, use that number. Yeah, so OCR and AQA will be slightly different in Edexcel, but use the number that they give you. Okay. Are we happy? I hope so, because we're going to get trickier. We're going to limiting reagents, which means that this stuff needs to be secure because now we're going to apply this stuff to just slightly trickier stuff. Again, it's not overly complicated. It's just about working systematically so that you're not trying to rush to the end. Okay. So many mistakes and so much confusion comes from trying to just do everything simultaneously, just work through the steps. Um, Yes, for ideal gas equation, always convert to Kelvin. Really, the only time that you shouldn't convert to Kelvin is when we are doing calorimetry calculations. So when it's Q equals MC delta T, a common mistake that students make for delta T is adding 273, but whether you've got degrees or Kelvin, delta T, which is a difference, is the same. So that's the only place really that it doesn't need to be Kelvin, but everywhere else, Kelvin should be there. Limiting reagents is within kind of stoichiometric relationships. Okay, often it's implied, like lots of specifications don't even necessarily say limiting reagents, but then you'll see them in exam questions. So we definitely need to know how to deal with them. Okay, so when it comes to most chemical reactions that we're doing in real life, so if you're in a lab, you don't add stoichiometric amounts. Okay, so for example, here where we say, oh, for 15 kilograms of calcium carbonate, we're going to add exactly 60 decimeters cubed of HCl. You wouldn't do that. You would put one of those species in excess because then that makes sure that all of the other reactant has reacted. Okay, so one reagent or one reactant is going to be limiting, so not enough, and the other one is going to be in excess, so too much, to make sure that all of the limiting reagent reacts. Okay, and so the limiting reagent, the one that you don't have enough of, that's going to determine how much product you can make, right? Because you can only make as much as your least amount. So let's start nice and straightforward by just figuring out which reactant is in excess. Okay, absolutely. Use the one with the less moles or with the fewer moles, but there's kind of sometimes an extra step to that. So stick with me. So for this one, we just want to know which reactant is in excess. And so to do that, we'll just find the moles we'll start by finding the moles for each. So moles of HCl, and side note, whenever they give you enough information to find moles for two things, it means they want you to find out which one is limiting and which one is in excess. Okay? Otherwise, they'll just give you the moles for one of them, the one that we care about. So, moles of HCl, that's your concentration times volume. So 0.0150 times 25 over 1,000, which is, someone tell me. I got this. Please tell me if you disagree. Perfect. Thank you, Felicity. Thank you, Ayan. Great. Moles of NaOH. Again, that's also a solution. Thank you, Afaf. So that's also going to be concentration times volume. So 0.02 times 20 over 1,000. I really hope I can do this in my head. I want to say 4 times 10 to the minus 4. If it's not, I'm going to be very embarrassed. Yeah, great. And I'm going to keep it to 3 significant figures just to be consistent. Okay. Now, before just jumping to saying which of these reactants is in excess, we need to double check the stoichiometry. We need to check the ratios, okay? Because it's not always just which is the biggest number, because if they react in like a 2-to-1 or whatever ratio, then that's going to affect which one is the limiting reagent and which one is in excess. So here, because the HCl and the NaOH react in a 1-to-1 ratio, we can just look at which one is bigger. In this case, the NaOH is greater, so the NaOH is in excess. Okay. Quick note, sometimes, just because I don't want to confuse you in the future, instead of writing excess, because as chemists we like symbols and numbers a bit more than words, often instead of excess, I'll just write XS. So if I do that, that's what I'm talking about. Okay, not extra small, just excess. Okay. Next example, Would they give the equation? It depends on the reaction, and that's a really, really good question. So here, because this is a standard acid-base reaction, they wouldn't have to give you that equation. Okay, so if it's a reaction that you're expected to know, they won't give it to you. But if it's not one that you're expected to know, then they would have to give it to you. Okay, or sometimes they will ask you to write the equation as one part of the question, and then you'll use that in the next step in this sort of calculation. But typically, if that's the case, there will be error carried forward. So if you balance the equation incorrectly, but your working for limiting reagent was correct based on that incorrect equation, you would still get the limiting marks, you just wouldn't get the equation mark. Okay. Let's go to the next example. Okay, again, if there are still any questions, make sure that you put them in. So another one, 50.0, you're welcome, 50.0 grams of SO2 reacts with 20.0 grams of oxygen, which is in excess. Again, we'll start by just finding the moles for each. So the moles for SO2, again, these are just masses. So what's that? Mass over MR. 50.0 over MR for SO2. Sulfur is 32. Is it 32.1 or just 32? I think it's 32.1. Plus the 32 from the two oxygens. So that gives us 64.1. Okay. If you disagree, please tell me. We've got 0.78. Thank you, Charlie. Beat me to it. Okay. Then for your moles of, what do we want? O2. Again, mass over MR. So 20 divided by, oh, actually, I agree. Let's put that 0 there to keep it consistent with three significant figures. 20.0 over 32.0 gives us 0.625. Thank you, Ayan. Okay. For this one, again, like I said before, we can't just now look at which of these two numbers are bigger. We have to first refer back to the balance symbol equation. These react in a 2-to-1 ratio, which means that however many moles of oxygen we have, twice as many moles of SO2 are going to react. So the easiest way, and you can just follow this all the time to figure out which one is limiting, is you just divide each moles by their coefficient. So for the SO2, because it's a 2, we're going to divide that number by 2. And for the O2, because it's an invisible 1, we're going to divide that number by 1. Okay, so now for the SO2, we end up with, I should put 0.39. And then for the O2, we get still 0.625. So which one is in excess? The O2 is in excess. So I divided by 2, because twice the SO2 is going to be consumed at like twice the rate of the oxygen, right? So if you've got let's say if you've got one oxygen, that's going to use two SO2s. So we're going to need more moles of SO2 than we would need oxygen. Does that make sense? So excess is the one with the biggest number of moles once we've divided by the coefficient. Okay, because dividing by the coefficient essentially brings them down to a 1-to-1 ratio. I hope that makes sense. Let me know if it doesn't. Okay, now really important point though, and we're going to get onto this as well in the next question. Once you've divided by the coefficient to figure out which is in excess, we never use those numbers again. Okay. So we don't then use that number to then say find out how many moles of SO3 you can make. We only, exactly, Ola. We only use these divided by the coefficient numbers to tell us which one is in excess, and then we do not use that number again. Okay. Let's do one more worked example, a trickier one. You use whatever the original moles were that you calculated. Okay, and we're going to do that in our next example. Okay, last worked example. Okay, and don't forget our lesson goes to 12:20, so our lessons are an hour and 20, so we've got still lots of time for you to do some practice. Okay, so worked example 3, we've got iron reacting with O2. What mass of iron 3 oxide is produced when 100.0 grams of iron reacts with 45 grams of oxygen? So first, in order to find out what mass of product we can make, we need to figure out which is the limiting reagent, because the limiting reagent is going to determine how much product we can make, right? So to do that, we'll follow the same steps as we did before. We'll find the moles. So let's start moles of iron, mass over mR. So that's 100 divided by what's iron? 55.8, which gives us 1.79. And then for the oxygen, again, oh, hello, pen. Thank you. For the oxygen, again, mass over mR. So 45 divided by 32. Oh, okay, Harlem, that's a great question. So whenever they give you information about both reactants, it means that you need to figure out which is the limiting one before you can figure out how much product you make. Right? So if you ever see a question where they say you've got this much of reactant A and this much of reactant B, you need to know which is the limiting, because the limiting one tells you how much product you can make. Okay. And they won't explicitly tell you, oh, find the limiting reagent first. It's just one of those things you need to spot if they give you both reactants. Okay. No problem. Okay. Agreed. 1.41. Again, we can't just use those numbers. In order to figure out which one is limiting, we need to use the coefficients. So for the iron, we're going to divide by 4 to get 0.4475. And then for the O2, we're going to divide by 3 to get 0.47. Okay. And remember, that's just bringing us down to our 1-to-1. So you can't see my hand, 1-to-1 ratio, so that we can actually see which one is limiting and which one is in excess. But then we're not going to use those numbers again. Okay. So here we can see the limiting reagent is the iron, which means that the iron, the moles of the iron, the moles of the iron will determine how much of the product, the iron 3 oxide, we can make. Okay, are you still with me? Wonderful. Okay, great. So now we've got now we know that the iron is limiting. Like I said, we're not using this number again. We're now just going to go back to our original moles and then use our stoichiometric relationships to find out how much product we can make. Okay. Zhive, do you have a particular question? Like which part is the sticking point for you? So we need to find which one is limiting, Ambajit, because we've been given the mass for both reactants. But how much product we can make is going to be based on the limiting reactant because we can only make as much as the one we've got the least of, right? So let's say, actually, no. I was trying to make a cake analogy, but I don't bake. So it wasn't going to be very helpful. Why do we go back? Because dividing by the coefficient, that's only to tell you to basically bring them down to a 1-to-1 ratio so that we can see which one is actually limiting and which one is actually in excess. So that's saying if they were 1-to-1, which one is in excess? But the actual moles that we've got based on the mass that we started with is 1.79. Okay, that's how many moles we've actually got in our pot. Okay, the division was just to figure out which was in excess. Okay, so now that we've got, you're very welcome. Now that we know that the iron is limiting, we can now go back to our stoichiometric relationships. Absolutely, Charlie. You'll always use the moles of the limiting reagent to then find the moles of your product. So looking at the iron to the iron 2 oxide, we can see that it's a 4-to-2 ratio, which is the same as a 2-to-1 ratio. Okay, which means that for every 4 moles of iron, we make 2 moles of iron oxide. So for every 2 moles of iron, we make 1 mole of iron oxide. So always half as much iron oxide as we have iron. Okay, so the moles of iron oxide are going to be half the moles of the iron because of the ratio, like we did earlier on. So we get 0.895. And then finally, to get the mass of the iron 2 oxide, that's just your nice straightforward moles times MR. So 0.895. And then the MR is 55.8 times 2 plus 16 times 3, which is, I got 159.6. Okay. How many significant figures would be appropriate here? I agree. 3 significant figures. So for the iron, we've got 4 significant figures. For the oxygen, we've got 3 significant figures. So we choose the least. So our answer should be 160 grams. Okay. So Felicity, we don't multiply by 4. So we don't use the balancing number, so the coefficient, when we're trying to find the MR. Okay, we only use that to find the ratio. So after we've done, okay, it's 4-to-2, so it's 2-to-1, we now don't use that 2 again. The MR is just for the iron 3 oxide. Oh, hang on. What's happened? You're absolutely right. I did mean to put 0.895 times 159.6. I got overexcited. Thank you. I started to think about significant figures and I couldn't contain myself. Okay. 142.8. Thank you. And so then to three significant figures, 143. Do we agree? I hope so. Wonderful. Okay. Okay. Let's do some practice. It does get a little bit harder than this, but I think it might be worth practicing what we've done so far before going a next level up. Seeing as we've just got over 10 minutes, I think that's a perfect amount of time just to practice what we've looked at. Okay, but any questions on these before we go to the practice? I'll do just a very, very quick recap. The moles of F2O3. Yes, so the moles of the iron 3 oxide are based on the moles of the iron. Okay, so once we did our calculation to find out which one was limiting, we found out that the iron was the limiting reagent. Okay, once we know that the iron is the limiting reagent, then that's going to determine how many moles of the product we can make. And then we just go back to what we were doing at the start of the lesson, which is just looking at the ratios. So it's a 4:2 or 2:1 ratio for the iron to the iron oxide. So however many moles of iron we've got, we divide by 2 to get to the moles of the iron oxide. Okay, you're very welcome. Okay, so just as a quick recap before we go to our final couple of questions, to find out the limiting reagent, we find the moles of both reactants and then we divide by the coefficient to then figure out which one is limiting and which one is in excess. Okay, if we're trying to find out how much product we're making, we'll take the moles of the limiting reagent and then we'll use our regular stoichiometric relationships to find out, using the ratio, how much product we can make. Okay, so let's have a go. So I would ignore, okay, unless you found that so easy and you really want to challenge yourself, I would ignore question number 3. Okay, I would have a go at question number 1 if you're feeling like, who, oh no, what's happening? And question number 2 if you feel like you're getting it and you're ready to apply it to one, like the one that we just did. Okay, just to make sure we've got time, I'm going to give you, let's say, 6 minutes, or maybe 5 to 6. Let's see how we do. So then that makes sure that we've still got time to go through the answers. Okay, again, do not do the last question unless you are feeling like an absolute superhero and it's felt so easy. Okay, any questions while you're working, please put them in the chat. Um, yes, let's assume that sulfur is just S. I know, and you know that it's what, S8, but let's treat it as S. Sorry, once you found what's limiting and what's excess, you use the limiting to find out the product. And remember, that's the original limiting moles, not when you've divided by something, if you did divide by something. Z-Hive, just by looking at the ratio. So once you've got which one's the limiting, you then look at the ratio between the limiting moles, the species, the limiting species, and the product. Back to the stoichiometric relationships we looked at the beginning. Okay, we'll definitely go through that together as well. We've got just about a minute left for you to work through whichever problem you're on. Um, for 3, you wouldn't use PV equals nRT because you're just dealing with masses. So you just use mass over MR. Ooh, for the third one, okay. So Charlie, it's asking for the total mass of gas. So that would be CO2, but when you work out what's in excess, that adds an extra level of challenge. Okay. Um, do we need more time or are we happy to go through questions 1 and 2 now? Okay. Um, um, so Aaliyah, it depends on what you found was the limiting reagent, but we'll go through it. Okay. For the first one, can you let me know which reagent did you find was in excess? Can you let me know in the chat? Okay. I agree, sulfur, and that's just by finding the moles for each. So for the, actually, let's do it here. So for the iron, moles of iron was 5 over 55.8, which should have come up to 0.0896. And then for the moles of the sulfur, 4 over 32.1, which should give 0.125. It's a 1-to-1 ratio, so we can just see that the sulfur is greater. Okay, great. Any questions here before we go to the slightly trickier, well, not even slightly trickier, much trickier question 2? Okay, so this question is like the last one, the last worked example that we did, where they're asking us to find out the mass of a product, but they've given us information about both reactants, which means to find out the mass of the product, we need to determine which is the limiting reagent, because that's going to determine how much product we can make. Okay, so we'll start by finding the moles of nitrogen. They've just given us masses. So we'll just do mass over MR. So that's 250. Question 2, probably really just 1 mark. So likely, actually, no, it wouldn't be multiple choice. It couldn't be because there's only two options. Um, it would probably be part of a longer question. But if it was by itself, I'd say a mark, maybe two if they add in something interesting. Okay. So moles of nitrogen, 250 divided by 28 should give us 8.93. And then for the hydrogen, we've got 200 over 2. Hang on, 200. Am I reading the right question? Oh no. There was, okay, great. I've changed the question. That's fine. So it gives us, what's that? 100? Oh my gosh. 200 over 2 is 100. Yes. There we go. Okay. So really, it's quite obvious here which one is in excess and which one is limiting, but we should always double check anyway and show our working for double checking. So we'll divide both by their coefficients. For nitrogen, that's an invisible 1 to give us 8.93, and for hydrogen, that's 3 to give us 33.3, okay, moles. So obviously the limiting reagent is the nitrogen. Okay. Once we know what the limiting reagent is, we then use that to find the moles of your product. So we need to look at our ratio. The ratio between the nitrogen and the ammonia is 1 to 2. Okay. So if we have whatever the moles of nitrogen are, we're going to have to double to find the moles of ammonia. So that's 8.93 times 2. Okay. 17.86. And so then the mass of ammonia. Oh, we've got lots of different answers here. So let's see. Mass of ammonia, moles times MR. So 17.86 multiplied by 17. 303.62. How many significant figures would be appropriate? Yeah, well done. 304 grams. Wonderful. Okay, this one would be, I would say 2 to 3 marks. Okay, do we have any questions here? I see that there's a couple that didn't get 304. Can you spot just from the working here why? Oh no, no, you're fine. So make sure you're following the steps, moles for both, find out which one is limiting, use the limiting to find out the product. Um, Amberjeet, what would happen if you use the element in excess? You would be incorrect, ultimately. Okay, because the reactant in excess is going to tell us, is going to suggest that we can make way more product than we actually can, because the limiting reagent is going to run out way before we've made that much product. Okay. Um, question 3, if you're interested, and then you can maybe work towards it to have a go in your work pack. Question 3, the answer is 210 grams. Oh, thank you, Lily. Oh my gosh. We're out of time. Should we, well, should we keep going to 12:30 and just, do you want me to show you? I really want to show you question three. Let's do it. Okay. Is anyone going to, if you're going to stay for question three, then I'll show you. So tell, like, if I get enough yeses, then we'll stay. Okay. All right. Okay. Question three is a bit of a crazy one, but we'll do it anyway. Again, we'll start off in exactly the same way. Oh, wow. Everyone's saying, okay, wonderful. We'll start off in exactly the same way as we did before. So we want to find out the total mass of gas produced. That is a massive, massive hint that there's going to be more than one gas present. Because if it was just one gas, they would just say calculate the total mass of carbon dioxide. It didn't say that. So that's your first hint that they're going to do something weird. Okay. But we'll start off in exactly the same way. We'll figure out which is our limiting reagent. So moles of our iron oxide, mass over MR. So 200 over, what did we have for our MR for iron 2 oxide before? Let me just go back and check so we'd have to work it out again. 159.6. Thank you, Ayan. Oh, where's my calculator? Okay, so 200, we get, oh gosh, 1.25. Okay, great. For our moles of carbon monoxide, 150 over 12 plus 16, 28. 5.36. Do we agree? Okay. So those are our moles. Thank you. To figure out which one is limiting, we're going to divide by the coefficient. So for the iron 2 oxide, that's divided by 1. And then for the carbon monoxide, that's divided by 3, which gives us 1.79. So that tells us that the iron 2 oxide is limiting. Okay, but again, we kind of knew that already from the weird way that the question was worded. We knew that the CO had to be in excess because we know some's going to be left over at the end, which is why it's the total mass of gas, not just the total mass of carbon dioxide. Okay, so now we're going to do the next bit in two stages. We're first going to find out what mass of carbon dioxide we can make, but then we need to find out what mass of carbon monoxide is going to be left over. Okay, so the moles of carbon dioxide that we can make is just based on the ratio. So it's a 1:3 ratio. Oops, oh my gosh. 1:3 ratio between our limiting reagent and the carbon dioxide. So that's going to be 1.2, oh my gosh, 1.25 times 3, which is 3.75. Okay. And so then the mass of carbon dioxide, 3.75 times 44 equals something. 165 grams. Okay. But because the CO was in excess, that means that there's going to be some left over. Okay. So we started with 5.36 grams. Okay. Lovely, great way. We started with 5.36 grams of carbon monoxide. Now the iron 3 oxide is going to be used up, okay? 1.25 times 3, so 3.75 moles of iron 3 oxide are going to be used up. Sorry, of carbon monoxide are going to be used up. Because if 1.25 grams of iron 2, there, let me pause. If 1.25 moles of iron 3 oxide are being used, then because of this 1:3 ratio, that means that 3.75 moles of CO is going to be used. Okay, so the moles of CO that are going to be left over are going to be 5.36 minus 3.75 moles, which is 1.61. And so the mass of carbon monoxide left over, 1.61 times 28, 45. So our total mass of gas is 165 plus 45, which is 210. Okay. Thank you, Saya. Or Saya. Sorry if I pronounced your name wrong. Please tell me which way. Okay. We know how many significant figures based on the question. So we use the least number of significant figures in the question. So here, 200 grams is 3 significant figures. 150 is 3 significant figures. So our answer, 3 significant figures. 3.75 is the moles. That is the number of moles of carbon dioxide, but it's also the number of moles of carbon monoxide that reacts with the iron 3 oxide. Because if 1.25 moles of iron 3 oxide are being used, then 3 times as many moles of carbon monoxide moles, have I said moles too many times, have been used. Okay. Any final questions? Okay. I would recommend having a go at this question all over again. Okay. So maybe print out the workbook again or go to get the page up again and then have a go from scratch. Okay. But for now, I will see you on when's our next lesson? Friday. And on Friday, we're sticking with calculations, my favorite type of calculation, your favorite type of calculation. Say it with me. Titrations. Yay. I would recommend doing the homework today. Okay. The homework is not just on the stoichiometric relationships that we looked at today. It's also just based on some other practice for calculations from year 12 as well. Okay. We are going to be doing some organic chemistry towards the end. I can't remember which lesson. I will double check, okay, and I'll let you know next lesson, okay? But there's definitely some organic in there with some isomerism for sure, okay? See you on Friday. Really, really, really well done, okay? And have a lovely rest of your day. Don't forget to do your homework, okay? Bye. Bye.